Today we're going to look at section 4.3 out of the textbook. So first recall a couple of items that we've already done. If we have a matrix A, we talked last time about the column space and how that's the span of the columns of A. That is something we've seen before. Last time we talked about the basis, how to find a basis. And remember, a basis is the smallest possible generating set. It's a linearly independent generating set. How did we find the basis? We took A and we found the pivot columns. We get the pivot columns by row reducing down to echelon form. That tells us where the pivot columns are. Then once we've identified which columns are pivot columns, we go back to our original matrix A and pull out those corresponding columns. That is the basis. The rank is the number of elements in that basis, which is also called the dimension. It's the number of pivot rows, or it's also equal to the number of pivot columns. That was the rank of A. Note that the rank of any matrix is the dimension of its column space. Those were ideas we saw last time. Another thing to recall. If we have any matrix A, we talked about the null space being the set of solutions to AX equals 0. So we saw how to find the null space and how to find a generating set for the null space. That's by solving for AX equals 0 and putting the solution into the vector form. A basis for the null space can be found by finding that general solution in the same way. The number of vectors in the basis is the number of non-pivot columns. So remember when we looked at this, we talked about being free variables. Well, that number of free variables, that's the size of the basis of the null space. So when you're solving for x equals 0, what you're actually doing is you're finding a basis for the null space for all of the things that turn into 0 when you multiply them by that matrix. And we had seen the idea before of the nullity of A being the number of non-pivot columns. So this gives us the idea that the nullity of any matrix A is the dimension of its null space. Again, bringing together the ideas of the nullity, the dimension, and the null space of a matrix. So let's look at an example of how we can pull these ideas together. So the idea here, the core idea here, is to know that the dimension of the column space plus the dimension of the null space is equal to the number of columns in your matrix. So here I'm giving you a matrix. I'm telling you that that is a basis for the column space. And I want you to verify that that's a basis for the null space. Well, from what I just said, that the dimension of the column space plus the dimension of the null space has to equal the number of columns in your matrix. So note that the basis for the column space is 2. We have 4 columns in our matrix. So we would expect 2 entries in 2 vectors in the basis for the null space. So that's what we have there. So that seems to be right. But now we want to verify that those 2 vectors are a basis for the null space. If you remember from last time, if we want to verify something is a basis for the null space, we have to do 3 things. We have to show the vectors are in the null space. We have to show that the 2 vectors in what we claim are the basis are linearly independent. And finally, we have to show that the dimension is equal to the number of vectors. So we're going to take these 3 things in turn and show that they are true. First off, show that those vectors are in the null space. So how do we show something is in the null space? Well, to see if something is in the null space, we can take our matrix and just multiply it by the vector. Because by definition, something being in the null space means that when you multiply it by that matrix, it turns into 0. So let's recopy our matrix down here. 1, 2, 1, 2, 2, 1, 1, 2, and 2, 3, 4. This is looking at the first item. Multiply it by the matrix, or the vector we have, minus 1, 0, 1, 0. And what do we get? We get minus 1 plus 0 plus 1 plus 0. For our second row, we get minus 1 plus 0 plus 1 plus 0. Then we get minus 2 plus 0 plus 2 plus 0. That equals 0, 0, 0. So our first vector is in the basis, or is in the space. It is something that, when you multiply by the matrix, turns it into 0. So it's in the space we're interested in. What about our second one? Again, we have to test if that is in our space. Our space is the null space, so we're just saying, does this turn into 0? And what do we get when we multiply these? We get minus 1, plus 0, plus 2. We get minus 1, minus 2, plus 0, plus 3. And minus 2, minus 4. Sorry. Minus 2, plus 0, plus 4. And that equals 0, 0, 0. So again, both of those two calculations show that the two vectors that we claim are our basis are actually in the space. That's the first step. So both vectors are in the null space of A. Our first step is done. Second, are they linearly independent? Well, hopefully by this point you should be able to see that if you have two vectors that are not a multiple of each other, they are linearly independent. So two vectors are not multiples of each other. So they are linearly independent. So that's done. Now the third one is saying, if we go back to here, it says to show that the dimension of our vector space is equal to the number of vectors. Here, what is the dimension? The dimension of the null space is equal to the number of columns minus the dimension of the column space. So we know that the dimension of the null space of A is equal to the number of columns of A minus the dimension of the column space of A. We can see that there are 4 columns in A. We were told that the dimension of the column space of A is 2, so that's 2. So the dimension of the space we're looking for is 2. We have 2 variables, or 2 vectors. So the number of vectors in B is equal to the dimension of the null space of A. That's what we have to check. All 3 conditions are satisfied. That all implies that B is a basis for the null space of A. And notice in this case, I didn't even have to calculate the null space. Just being able to show those 3 conditions show me that it is a basis for the null space. Using one of the key ideas that the dimension of the null space is equal to the number of columns minus the dimension of the column space. Next idea. We've talked about a column space. What about rows? There is also this idea of a row space. And the row space of a matrix is the span of its rows, denoted by row of A. What you do is you take the rows out of your matrix, flip them around so that they're in the vector form we're interested in, and look at the span. So the row of A is actually equal to the span of those three vectors. Theorem 4.8 says that the non-zero rows of the reduced row echelon form of a matrix are a basis for the row space of the matrix. And the dimension of the row space equals the rank of the matrix. So we're going to look at this just a little bit closer here and see what this means. If you have a matrix like this, and you go through all the trouble of row reducing it, bring it to row reduced echelon form, and you get this. Now, what is the basis for the row space? Find your pivot entries, and then take those rows from your row reduced version, and that is the basis. So, first off, the basis for the row space of A. The basis for the row space of A comes from your row reduced echelon form. So the basis for the row space of A is equal to 1, 0, 0 minus 4 over 3, 7 over 3. Your second row, 0, 1, 0, 2 over 3 minus 2 over 3. And your final row, 0, 0, 1, 1 over 3, and minus 1 over 3. There is your basis for the row space. You don't need the third one because it's already taken care of. What about your basis for the column space? Well, to get the column space, remember what we said? We take our columns that have pivot entries, and we take the corresponding columns from our original. So the basis for the column space is 1, 1, minus 1, 0. The second one, 2, 2, minus 1, 1. And the third column, 0, 3, 1, 1. That is a basis for the column space. Notice the row space has dimension 3. The column space has dimension 3. The dimension of a row space and a column space are always the same. But now, what about the third one? The null space. How do we find the null space? Well, fortunately in this case, we've been given the row reduced echelon form, so we can figure it out from there. Our row reduced echelon form looked like this. Just to rewrite it again. And minus 4 over 3, 0, and that is our row reduced echelon form. So again, if we look at this now, we have 3 variables that are basic variables and 2 free variables. Our equations are going to be x1 minus 4 over 3 x4 plus 7 over 3 x5 equals 0. And similarly for my other variables, for my other rows, that's not a plus, that's a minus. 2 over 3 x5 equals 0. x3 plus 1/3 x4 minus 1/3 x5 equals 0. And my x4 and x5 are my free variables, so let's write them like that to make sure I don't forget them. Rewrite these equations as x1 equals 4 over 3 x4 minus 7 over 3 x5. Just put them in the proper form and make it a little bit easier so we don't get things mixed up. x4 plus 1/3 x5, x4 equals x4, x5 equals x5. Now that we have it in this form, we can write our general solution, x1, x2, x3, x4, and x5. We have two free variables, x4 and x5. So our solution is going to look like that. And for the coefficients, we now just pull them out of our equations. 4/3 minus 2/3 minus 1/3, 1 and 0. And for x5, we have minus 7/3, 2/3, 1/3, 0 and 1. Now that I have this, this just gives me my basis. So my basis for the null space of A are just these two vectors. It's 4/3 minus 2/3 minus 1/3, 1, 0. And my second, minus 7/3, 2/3, 1/3, 0, and 1. There is my basis for the null space. Notice I have two vectors in the basis for the null space. So the dimension of the null space is 2. I had 3 vectors in the dimension of the column space. So the dimension of the column space is 3. 2 plus 3 equals 5. 5 columns in my original matrix. You always have that relationship. Couple of facts. The column space of a matrix is just the row space of the transpose. So if you take a look at how the matrix is defined, how the column space is defined, you can see why that's true. The rank of any matrix equals the rank of its transpose. And you can see again, if you play with a matrix and its transpose, you can see why that would be true. Which leads us to theorem 4.9, where we talk about a subspace of a subspace, so kind of nested subspaces. If you have two subspaces with one inside the other, then the dimension of V is less than or equal to the dimension of W when V is contained in W. So that's probably not too surprising. If you have one thing inside another, the size of it is somewhat less. We also have this property that if the dimensions are equal, then that means the subspaces are themselves equal. Dimension not only describes kind of the size, but it tells you a little bit something about its content as well. So if you have two subspaces, one inside the other, with the dimension of them being the same, you know right away that they are the exact same thing. And finally, for section 4.3, here are a few